Hi guys, so I'm going to teach you about chi-square. So this will be a good video to review if you were absent or maybe helping out with 8th grade tours on the day that I went over chi-square. So I do want you to have a spot in your notebook for chi-square. So chi-square is this x. It's a lowercase Greek letter with the square, lowercase x in the Greek. You do need your AP formula sheet as well, but we won't use that for a little bit. Chi-square formula as found on the AP sheet, formula sheet right here on the front. I am going to write that in my notebook. Equals sigma, or the sum of O, not 0, minus E squared over E. And in this case, O means observed and E means expected. So when you're calculating an observed, actually, let's go ahead and write that down. So O equals observed. This is typically your treatment. And expected, E is expected. And this is, or can be, your control. Okay. So the first thing that you want to do is actually determine or review what your hypothesis is for your experiment. So in the case of the onion experiment, our hypothesis could have been, and you should use, when you're doing your lab report, you should use your hypothesis. But one hypothesis could be that the onions grown in the caffeine will have more or greater, more higher number, more cells in mitosis, and that would indicate rapid growth. So if we were to count the number of cells in the onions, the ones grown in the caffeine would have more cells in mitosis and less in interphase, and therefore that would indicate rapid growth. So this is our experimental hypothesis. You can have more than one hypothesis for an experiment. We do typically just focus on one, but you really could have more than one. So with your hypothesis, now when we're doing a statistical test, and that's what chi-square is, it's a type of statistical test that we can apply to our data. When we're doing a statistical test, it's not telling us anything about our hypothesis. Instead, it's telling us about something called a null hypothesis. And your null hypothesis can be abbreviated with a big H and a 0 subscript for a not hypothesis, null hypothesis. And a null hypothesis is that there is no significant association between caffeine and onion root growth. So this means that no matter what we find, even if there looks to be a difference, when we compare our numbers and do our statistical tests, there is no difference between, there's no significant association. Any difference that might be there would be based on perhaps chance or an error, sampling error even. So the next thing that we're going to do is we are going to collect our data. So we'll need to run our experiment, and this is what you're going to do on Monday in class. So we need a raw data table. For this example, I'm actually just going to give you data. So a raw data table. So our water, our onion grown in water is going to have some cells, and we're going to count the number of cells in interphase. Should have made my table a little bit bigger. And we're going to count the number of cells in mitosis. So any of the prophase, metaphase, anaphase any of that. And then we're going to have a total. Okay, so I'm going to count my onion that's grown in water and my onion that's grown in caffeine. And when I do that, let's say I do that and I counted 125 cells in interface and 128 cells in mitosis, and that gives me 153 total. But when I do the same thing and I calculate and I count for my onion, I get 140 cells in caffeine and only 10 in interface. And so my total is my total is 150. And so when I look at this, it may look like my caffeine perhaps stunted the growth of the onion. And so just looking at the raw data, students might say that, oh, the onions that are grown in the caffeine, they don't have more cells in mitosis. So the caffeine is slowing the growth. But we're going to look at this null hypothesis. We're going to run this chi-square test, and we're going to determine if there is statistically a difference. It looks like visually there is a difference, but we're going to determine it statistically. So this formula up here it looks really scary. It looks very complicated, but if you make a table, what I call a chi-square table, it takes you step by step through what you need to do to solve the problem. So that's what we're going to do next. We're going to make a chi-square table. And to do the chi-square table, the first thing we need to do is write our two variables down, and our variables our dependent variables are how many cells are in interphase and how many cells are in mitosis. And then we're going to have a column for the O, the observed. Okay, and this is going to be my treatment sample, so my treatment, my caffeine. And then I'm going to have a column for the E, the expected. This is my control or my water. Okay. And then I'm going to have a column for the O minus E, the O minus E squared, and then the O minus E squared divided by E. So now I have a column that walks me through almost all of my chi-square steps, okay? So for my treatment values, I can just pull these right off of my raw data table. So I had 140 cells in the interface in the caffeine, so I just moved that down. Then I had 10 cells in the mitosis, so that brought my total to 150. So you might think that, oh, we can just bring these down as well, but the problem is that we really need our two totals to match each other. They need to equal in order to be able to run the statistical test. So what we're going to need to do is translate this data and convert it into numbers that equal 150. So in order to do that, we're going to take 125 divided by 153. Okay, so 125 divided by 153, so I had 125 cells in interface out of 153 cells total, and that gives me 0.817. And then I'm going to multiply that times, well, what if I only counted 150 cells? So then that would give me 122.25 cells. So if I only counted 150 cells, then I would only expect about 122 of them to be in interface. So now I'm going to take that value and put that here. And I'm going to do the same thing for my mitosis cells. So I'm going to take the 28 divided by 153. I'm going to get 0.183. So that's my percentage of the total 153 that were in mitosis. I'm going to multiply that times 150 so that if I only counted 150 cells, that's what I would get. And I am going to get 27.45 cells. So if I counted only 150 cells, if I only had 150 cells to count in the water, then I would expect about 27 of them to be in mitosis. And now when I add these two numbers up, now I get 150. So that is awesome, and we can proceed. So the next thing that I'm going to do is take my O minus my E. So I'm going to take 140 minus 122.25, and I'm going to get 17.75. And then I'm going to take the 10 minus the 27.45, and I'm going to get negative 17 point, that's supposed to be 4. Nope, that was a 7.45. Okay, so now I'm going to square both of those. So 17.75 squared is 315.06, and then negative 304.5. And so now I'm going to take each of these numbers, because I have the O minus E squared, and I'm going to divide by the E. So I'm going to take 315.06, and I'm going to divide by the E right here, 122.25, and that's going to give me 2.6. And then I'm going to do 304.5 divided by 27.45, and that's going to give me 11.09. And now I've dealt with everything in my formula that's up here except for this sigma. Okay, so now I need to deal with that sigma. And when I deal with that sigma, all I need to do to deal with that is to add these two up. So when I add them up, so 2.6 plus 11.09 equals 13.69. That is my chi-square. Okay, so chi-square equals 13.69. Okay, now who cares? What do I do with that number now? Okay, I need to figure out what happens to this number. What do I do with it to determine if we have statistical significance? In order to take this number, I need this chi-square table. So notice that it's right here on your formula sheet. It's given to you. It's not something that you would ever memorize. Statisticians don't even memorize this, although you could use it enough that you have the values memorized. But we need to get our critical value off of here. And the critical value is our chi-square that we're going to compare our chi-square to. But we need to determine something called a degree of freedom and a p-value. Okay, so the first thing that I like to do is I like to determine my p-value. And so my p-value for biology is typically 5% or 0.05. So we like to use the 0.05 in biology, and because that means that there is only a 5% probability that any deviation, any differences is due to chance. So that's an acceptable level for us. We can say, all right, I'm okay as a scientist with only 5% of my work being up to chance. Okay, anything more than that, I'm not happy with. The 0.01 would mean that there would be a 1% probability that any deviation is due to chance. And when you're talking about living organisms, it's just not realistic typically to say with such a small, to go for such a small statistic. It's more realistic to say that there is some chance and we're willing to accept 5%. So now we know what row we're working on, but we still need to know which column to get our critical value. And so in order to figure out the column, we need to know a degree of freedom. And the degree of freedom called the DF, or abbreviated the DF. This is, the formula for that is n minus 1, where n equals the number of treatments. And in this case, our treatments in this lab are interphase and mitosis. So that would be 2. Interphase and mitosis. We have 2 for our n, so our n would be 2, and we're going to minus 1 because that's our formula, so our degrees of freedom would be 1. So now that we know that our p-value is 0.05 and our degrees of freedom is 1, our critical value equals 3.84. So now we compare our critical value to our chi-square. And any time that chi-square is greater than or equal to the critical value, we reject the null hypothesis. Ooh, you can't see what I'm writing. So this means that we reject the idea, the null hypothesis, that there is no significant association. So we reject, we reject our null hypothesis that there is no significant association. So that means that there is a significant association, that caffeine does have an effect on our growth. Now, was this a positive or a negative growth? Well, we got less, so this would be a negative growth. So caffeine retarded the growth of the onions. The last thing that I want to point out is just that if your chi-square is less than the critical value, you do not, what that means is you accept the null. There are some other statistical words, but in biology we can accept the null, and that means that our hypothesis, our testing hypothesis, is not supported. Okay, we do not ever prove a hypothesis correct. So this case, even though we reject the null and we're not proving our original hypothesis. Okay, so remember that we do not ever prove hypotheses. All right, so that's it. You'll practice applying this in your onion lab when you collect the data. Everyone will have their individual chi-square test where you'll look at your individual caffeine, and then we will show some trends with class data as well. Okay, thanks so much.